All right, good afternoon. My name is Parimal Kopardekar, but my user-friendly name is PK, so you can call me PK. And I'm also happy that you all asked difficult questions to Jim, so I don't have to answer any one of those. I'm going to talk about how we think we can enable the civilian low-altitude airspace and particularly UAS operations by a construct that we are referring to as UAS traffic management, or UTM, which is analog to ATM, air traffic management. Let's see. Okay, here we go. So most of you know the airspace classification, but just a quick refresher. We are focused on the Class G airspace, the low altitude, 2,000 feet and below. Most of these operations that we are referring here, low altitude operations, are likely to occur in 400 and 500 feet, but they could go up to 2,000 feet as we know right now. They could change, but that's the focus of our work right now. So quick outline, I'll talk about the motivation, why we are doing this work, what's the sense of urgency, which all you know, so I don't really need to talk much about that. What are the key design functionality, architecture options and alternatives, some demonstration options and business models and partnership opportunities. Sounds like every one of them have a partnership as a slide, so I felt I should have one too. And our next steps. You all know that there are lots of applications, so I don't need to talk about those, but what really the key here is many of these operations will occur at the low altitude, which is where the businesses are going to thrive in our mind. And these are not going to be only UAS, there will be personal air vehicles as well. And we really need some kind of infrastructure to safely accommodate these operations. That's our goal. There's, of course, global interest that's seen here. Fundamentally, what we are after is this lesson from history. If you look at 1956, the mid-air collision over Grand Canyon is how the air traffic management started. So we began to think about this and said we really need to have a system in place so we really don't repeat the history. That's kind of the main motivation why we started this research and development. This is our notional scenario. I don't think I need to spend too much time here, but we really are talking about two different systems. There is a persistent system and a portable system. Portable system is going to go from one landscape to another landscape. You can imagine something at the back of the truck with maybe low altitude radar, maybe some internet-based app that you just saw. But that will go from landscape to landscape. And really, what we are attempting to do here is accommodate heterogeneous operations and heterogeneous vehicles and heterogeneous businesses in the same airspace. So you can see search and rescue and surveillance of key assets and picture taking and UAV following car and cargo delivery and all kinds of things. So there is obviously sense of urgency. You know, the co-op process is very limiting, as you all are frustrated with this. As we know, we need to have a system of rules and regulations urgently. So we have really two goals. One is the near-term goal is to try to enable these operations within 5 years, as soon as possible, but within 5 years. And second long-term goal is to enable the highest safety for these operations, which are going to increase in the massive scope. So we need to accommodate these operations in 10 to 15 years. We see a tremendous, basically, scale of operations. So let's say if we are an operator, if you're a drone operator, UAV operator, what would you like to know? You know, fundamentally, what you want to know from the perspective of entering into that airspace is that airspace open or closed? So you can see that our talk here is changing the context from vehicle to a single mission to entire airspace. So that's the idea here. We want to know whether the airspace is open or closed right now and in the near future, whether which airspace can I operate in and which airspace should I avoid. Will there be anybody else in that airspace? At the same time, I will be. What should I do if I need to change the trajectory? You saw the drone deploy, so there's a good example there. How to manage a contingency, and we'll talk about the different contingencies. And who should operate this airspace? So this is another interesting question, and how should we operate that airspace? So let's look at the design functionality that we think we ought to have. First one is airspace management, and this term geofencing. You may have heard this term before. Idea is to fence up things where we need to keep them clean. So there's an airspace that is fenced up, and you need to operate inside that airspace. Rest of the airspace you avoid. There's going to be interesting weather and wind challenges from our own research and the trajectories and integration of weather and wind. We found out that some of these vehicles will fly backwards if you have wind of 15, 20 knots. So we really need to understand how these vehicles will operate in the context of winds. Which winds are safer, and when do you actually say that these airspace is open given the context of wind? New York City, if you really wanted to operate in New York City, which I'm not saying we should, but the eddy currents that exist between the alleyways are interesting challenges. So then predict and manage congestion is another thing. Eventually, we are going to have large-scale operations. So how do we predict congestion, demand and capacity imbalance, which is what we typically do for classical air traffic control? Then terrain and man-made objects, database and avoidance, we all know where to find that, and we know how to integrate with that. And we want to maintain a safe separation and then allow only authenticated operations, that point that was made before. Some question, why do I need to have a system? Why do I need a system to begin with? And the analogy there is, you have a car, whether it's self-driving or person driving, human driving a car, doesn't really eliminate the need for roads or traffic lights or rules. So that's the same thing. We need to have some kind of a system that will enable us these operations at low altitude. So examples, and I won't talk about all of them, but authentication, some kind of authentication, rules of the road for airspace, altitude for direction perhaps in the beginning stages, areas we want to avoid, CNS. There are lots of options for communication, navigation, surveillance, low altitude radar, there's a cell phone coverage, a whole bunch of other options are available. Separation management functions, there is lots of effort that's going on. So we are not focused, this particular effort is not focused on sense and avoid, but more on the airspace aspects and the weather integration. Contingency management, this is an important aspect. A lot of folks argue, and we have good discussions about that, how much contingency management we should build into this system. So we really want to not only consider the lost link scenario and the rogue operations and crossing over the geofences and what to do when those things happen, but we also want to think about what could we do if there's a potential 911 kind of a scenario, and we have to have this direction that says everybody should land to figure out who is still a rogue operator in that airspace. So we need to have ability to get to that point of some way. Congestion prediction, figuring out how do we actually predict congestion in certain airspace, what to do with it, by scheduling or reservations of the airspace. And overall design, obviously we don't want to make the design of the UTM so cumbersome that it will be expensive, prohibitively expensive to operate. And then we need to continuously collect data about performance monitoring with respect to the geofencing and the trajectory prediction and the trajectory conformance. And ultimately, we really have to worry about the last 50 feet operation and the first 50 feet operation. How do we descend and ascend in the presence of moving objects, grandma mowing the lawn and all kinds of things, kids playing soccer. So there's a body of work that's going on in that direction as well. So I won't go into too much detail here, but basically we need some of these key characteristics in terms of ability to support diverse mission, business trajectories. We need to be able to provide reliable communication, navigation of some kind, must be able to accommodate all kinds of vehicles who are autonomous, who are not autonomous, and must be able to provide some kind of congestion management, route planning capabilities. So this is a sort of overall design option, one of the options anyways. Ultimately, we want fully autonomous city, IEEE term, if you will, that goes into that, which self-configuration, self-optimization, self-protection, and self-healing of the system that is going to take care of this. So sort of an autonomous system, if you will, which will have all these features that I mentioned before, which is connected to the wind, real-time wind prediction, airspace constraints, any community-based concerns about noise, sensitive areas, privacy, so you can do the geofencing and dynamically adjust the geofencing and such. Then if you are an operator, so how do you access the UTM? Ultimately, we want this to be a cloud-based service where users access through, all users access through internet. They will be able to generate and file a nominal trajectory, adjust the trajectory in case of congestion or some preoccupation of the airspace, verify for all these conflicts and things that you need to avoid, verify for usable airspace, verify for winds, and any bad weather situations, monitor trajectory progress and adjust the trajectory as necessary. So these are the functions that will be afforded inside that. If you are a UTM manager, what would you do? So if you're a manager of this system, so you will set up the design of the airspace, you will set up the functions so that the fleet operators as well as the singular vehicle operators can also use that airspace. Then it will be overall schedule-driven system to make sure that there are strategic deconflictions, at least in the beginning stages, and eventually it will be a lot more dynamic and agile, just like the air traffic management system we have. And largely, we want this to be managed by exception, so not a person, one single person watching every UAV in the sky. It's automatically, autonomously managed. So we conducted a workshop to get idea related to this concept, get feedback from folks. We had 145 non-NASA folks, a whole bunch of partners that have emerged. As part of this workshop, you can see all the happy faces that attended the workshop there. And the main findings about the workshop were there is overwhelmingly positive response about this construct of UTM, the strong support for NASA's ability to lead this, and many partners are ready to engage, and there is going to be an urgency to put this system in place. So how are we going to do forward from where we are? So the way we are going to architect this approach is to construct number of builds, which will evolve over time. And the first build the goal is to mostly show the information. So it's a static display of the geofence, or airspace definition, altitude for right altitude for direction, and basic scheduling and such. And then next one will be the dynamic adjustment. So that will be the build 2. Then build 3 will have contingency management, separation assessment, and the build 4 will be the large-scale contingencies. Now the question is, how do you want to participate? How will you want to participate in this? So we are going to set up ways where we will be doing the test of the builds, and we will be looking for folks to bring their missions and vehicles so that we will evolve the UTM builds, collect the data, and then demonstrate that the system can accommodate everybody in the same airspace at the same time. That's kind of the goal. So the goal is to enable these operations. There's pretty good support of the UTM construct. There is already a parallel in the form of air traffic management. Many partners are ready. We will be more towards autonomy. And there's going to be a partnership strategy that's forthcoming related to this. I'm open to any questions.
Hold on a moment. Everybody wants to hear this great question.
No, I've actually, I'm thinking, aren't you overcomplicating things? How, for example, do you want to do communication between the vehicles with this system? Or is it just defining airspaces and without any communication?
So the V2V communication should have to be based on needs. What are we doing V2V communication for? Are we passing the information about the weather in the front, or are we simply doing V2V communication for collision avoidance? So that's the construct that we have to define. Some operators will have V2V, others may not. So we want to accommodate both kinds of operators.
Okay, because in the car industry, this already has been done. You have a system called, you have ITS and car-to-car communication. The protocol has been defined. Also the hardware for that is ready. You have the 802.11p standard for the communication between vehicles. I think this is really overcomplicating it, and the things that they are putting in the cars, can easily be used in these systems like this. The cost will be low because the number of cars sold and that will have this technology on board will make it also very cost efficient. And I think if you're going to do it all over again, it's a waste of time. If there's already a system in place that can be adapted to these systems, because the systems we're talking about, 99%, are the vehicles that are operating at low height, probably have the same speeds as cars, maximum. and are operating in an area where they have to communicate with other devices and other, for example, cars or buildings. And that's exactly where this protocol, this ITS, this car-to-car communication, car-to-X communication, has been designed for.
Yeah, so I'm not sure I understand your point that we are overcomplicating, because there is more than just a communication. And as I said, we want to be as minimalistic as possible. Maybe it's not required at all, and I don't think I said that we need to have car-to-car or vehicle-to-vehicle communication. Fundamentally, this is about airspace management.
Yeah, but that's...
So ability to talk to the vehicles back and forth and monitor them is what's important, and maintain them in the airspace that we designate them to operate under.
But are they operating in airspace? Yes, well, due to law, and we have heard, of course, the FAA talk about that. But are they operating? Are they more operating in the airspace, or are they more operating in, for example, the space that we're living close to the ground? You know, in the future, plumbers will, for example, use the systems to check roofs, or everybody will have maybe a small pocket drone, and if you want to implement things in these, you have to regard them more like the things that we see around us than as airplanes.
So this is where it comes to whether it's going to be a congested airspace or not. If you're operating in an airspace that is not congested, it's on top of your roof, there's not going to be probably other folks running around there. So that is not an issue. But if you're operating in an airspace that's going to be congested, then yes. So if you have a zip code that a bunch of deliveries are coming, it's possible that there is going to be trajectories that are going to be crisscrossing. So who is going to be responsible for making sure that these heterogeneous trajectories are kept separated? That's kind of the airspace separated, right? So it's not just one vendor or one person who is...
No, but that's not what I'm saying. I'm saying cars that can... Oh, okay.
I don't want to, but we have to stay on schedule. We got a lot of people.
Well, we can talk more. I'd love to talk to you and make sure that we address the question. Thank you again, Patrick.